Hi, this is the beginning of course number 2, which covers chapters 11 to 20. Today we're starting chapter 11, so this is section lecture 1 of chapter 11. We'll talk about influence lines for frames. In chapter 10, we talked about influence lines for beams. We talked about we defined influence lines. We draw influence lines for different beams, for reactions, and for normal and shear. And we considered horizontal beams. So there is no normal force. So we only had normal reactions, shear, and moment. So now when we talk about frames, there will be reactions, normal force, shear, and then the moment for the influence lines. And as always, we'll, we'll start with the influence lines for reactions. I'm going to have a little bit of introduction, sorry about that, and then we're going to share the screen to solve some examples. So there will be introduction about influence lines of frames and then examples. So this is the outline for this chapter 11. Influence lines for frames. It is we draw the influence line of frames for the reactions at the supports. The shear and bending moment values change on any section due to the change of location of the load. So as the load moves, the values of shear and moment change. And this one, because of frames, because we have a combination of horizontal and vertical and maybe inclined members, so we have normal force. So we'll draw the reactions and then normal force influence lines for normal force, shear and bending moment at any section. We start with the reactions and then we move the loads at different locations and then we draw the influence lines for normal shear and bending moment due to different locations of the load. Where do we put the 1 ton when we draw the influence lines for reactions? If the beam is if the beam that has the load, if the beam under consideration does not have intermediate hinge, we put the influence line on the top of supports or top of columns, calculate the reactions in every time, then draw the influence line of reactions. In this case, the influence line of reaction we, we calculate for any beam for two different locations and connect them by a straight line. If the beam, in case the beam that has intermediate hinge, we put the influence line, the loads on the ends of the supports of the columns and also on the intermediate hinge and calculate the influence line of reactions. We calculate the reactions for every case and then draw the influence line for reactions. In this case, we draw the influence line for reactions at three different locations, columns or supports, and intermediate hinge, and connect them with a straight line. We're going to start with some examples. So I'm going to share the screen to show you the first example for influence lines for frames. So this is the first example for the shown For the for the shown frame, draw the influence line diagrams for the reactions. So we have the frame, 5 ton, two equal leg columns or two equal columns, 5 meter each, horizontal span 8 meters. So it's a hinge and roller, and we have 1 ton moving from the right side to the left side. Okay, so draw the influence line of reactions. We put the load, we calculate the reactions XA, YA, and YB. So we have XA, YA at A, YB at B, and we have that 1 ton moving from the right to the left from point B towards point A. Then solve the frame twice, and due to the location of the load in two different locations. And the easiest is to calculate above the columns or above the supports. So one case put the load on the top of the left support, and the other case put the load on the top of the right support. So when the load is on the top of the right support, 1 ton is taken fully by the left support. I'm sorry, taken fully by the left support, reaction is 0 and the X reaction is 0. When the load is placed or is standing on top of the right column, so one ton is taken fully by the right column vertical reaction. The other support has 0 reaction, 0 vertical and 0 horizontal. Okay, then we plot the points and draw the influence line diagrams. Okay, so influence line of XA is 0. It's 0, doesn't matter where the load is. Influence line of reaction XA is 0. Okay, influence line of YA is 1 when the load is at A, is 0 when the load is at B. Influence line of YB is 0 when the load is at A, 1 when the load is at B, so it's from 0 to 1. Influence line YA is from 1 to 0. Influence line of the support reaction XA equals 0 because it doesn't matter where the load is. X equals 0, it's a vertical load going down. Okay, example for the shown frame, draw the influence line diagrams for the reactions. So this is a 3-hinged frame, 2-hinged support, and the intermediate hinge on the top. We have the 1 ton moving from B to A, at 5-meter height, 8-meter. This is 8-meter span, 8-meter span. Same like the previous frame, but instead of having roller on the right, we had hinge on the right and intermediate hinge on the top, so it became 3-hinged support, or 3-hinged frame. And we want to calculate the influence line of reactions, influence line of YA, XA, YA, influence line of XB, YB. Okay, so this is the B, the frame with the reactions XA, YA, XB, YB. Sigma X equals 0, then XA equal XB. So it's only one unknown. So XA equal XB. We have only vertical force going down. Then the reactions at A and B are the same. XA equals XB. And we solve the frame twice. When the load is located in two different locations. And the easiest is to calculate at the support at the column. And the third location is to put the load on the top of the intermediate hinge. So three different locations. We calculate the reactions for the load at three different locations, and then we connect for every case. So influence line on A, the load is 1 ton, XA equal XB equal 0, YA equal 1, YB equal 0. When the load 1 ton is on B, 1 ton, then YB equal 1, XA equal XB equal 0, YA equal 0. When the load is on the intermediate hinge, 1, so the reactions, the vertical reactions are 0.5 and 0.5 from moment the right of the hinge. So this 0.5 by 4 equals this one by 5, so this one is 0.4. So the X reactions are plus 0.4 at A minus 0.4 at B. Then we plot the points and draw the influence line for reactions. The influence line of YA is 1, 0, and 0.5 and 0. Influence line of YB is 0, 0.5, and so 0.5 and 0. So YA equal 1 when the load is here, YA equal 0.5 when the load is on the top of the intermediate hinge, YA equals 0 when the load is on the top of the column on B, or at B. So 1 to 0.5 to 0 plus. Influence line of YB 0 when the load is here, plus 0.5 when the load is here, plus 1 when the load is here, so 0 to 0.5 to 1 plus. Influence line of XA or XB, when the load is here, it is 0, when the load is on the intermediate hinge, it's plus 4, when the load is at B equals 0 to 0 to plus 0.4 to 0. So this is the influence line of XA or XB. Okay, when we calculate, after we calculate and draw the influence line for reactions, we calculate and draw the influence line for normal shear and moment at any section. Okay, and then to make it easy, we divide the sections or classify the sections as follows. Section N, M, and K. Okay, and we have the cantilever 1 and point 2, which is the hinge connecting the right column to the beam. So we have one case, case number one, when the section is between the two supports, the section M, between the two supports. We divide the problem into two problems. When the load is left, it's right of the section, when the load is left of the section. So when the one ton moves from M to 1, when the one load is moving from M to 1, we calculate from the right. We put the load anywhere between 1 and M, we calculate from the right. Okay, so we have x, b, y, b, point 2 intermediate hinge. So let's say that this is 8 meters, 2 meters to M, 2 meters to the hinge, and 4 meters remaining. So when the load is between 1 and M, Nm equals minus xp, compression minus xp, Qm equals minus yb, mm equals yb multiplied by 6, minus x minus 5 multiplied by 8. When the load is moving from 2 to M or M to 2, we calculate from the left. We calculate from the left. When the load moves between M and 2, we calculate from the left. Then Nm equals minus xa, Qm equals y plus ya, and then mm equals ya minus 5 by 2, 2ya minus 5xa. For any section along the column A, we calculate one time, one ton. We calculate one time away from the column. So when the load is in a section K, we calculate one time left of K. So we calculate one time left of K. We have x, a, y, a. So Nk equals minus ya, Uk equals minus xa, and Mk equals minus 3xa. And the cantilever, like section N, deal with it like beams, calculate from the, when deal with it in the beam, where when the load is beyond section N, then normal equals shear equal moment equals 0. When the load for a section in the cantilever, we deal with it as beams. Before the section, the load equal normal, moment equal shear equal 0. After the section, when the load is here between 1 and n, shear equal constant equal 1, or constant equal minus 1. So here it's equal minus 1 when the cantilever is left, and here equal 1 plus 1 when the cantilever is on the right. Moment is 0 at the section, and the moment equals minus L at the three ends, which L is the length of the cantilever. The normal force location, tension is positive, negative compression is negative, shear positive left up and right down, negative left down and right up. Signs for moment, we just review what we know already. Positive sign when the tail of the moment is below, and negative when the tail is above. And for frames, we stand inside the frame and look at the different members, and this is how we calculate and put the size for frames. Important notes: when the one ton moves on a horizontal plane, on one horizontal, let's say only on AB, not on CD, it doesn't change the level. So the one ton moves from A to B or moves from C to D. We draw the inference line for the direction when the load is moving. If the one ton moves along AB, then we draw the inference line diagram for AB only. There is no inference line for CD. When the one ton moves on CD, we draw the inference line on CD, and there is no inference line for AB. Example to make it easy. For the shown frame, draw the influence line diagrams for the reactions, an influence line for normal shear and moment in the market at the market section, which are sections M, N, and G. So we have the frame like this, vertical leg, inclined leg, hinge or roller. At A, we have hinge, X, A, and Y, A. At B, we have roller, Y, B. It's not a link member, it's a column. We have the span of the beam. I mean, the distance between the support is 10 meters. The upper beam is 7 meters, 3 meters to the right cantilever and 2 meters to the left cantilever. The vertical column is 4. For this inclined one, it's 4 vertically, 3 horizontally, so it's 5 on the incline. Cosine equals 4 by 8 point, 4 by 5.8. Cosine equals to this theta. Cosine equals 1/6. To find the reactions, influence line for reactions, we put the load on at A, so YA equal 1, this X equals 0, YB equals 0. We put the load on right on B, which lines up with the tip of the right cantilever. The reaction is 1 at B. The reactions are 0 at B. So this is to the influence line of reactions. Okay, so from 1 to 0 and from 0 to 1. For section N, which is 4 meters from the left support, we have two cases. The one ton is between C and N, and the other case is 1 ton is between N and A. When the 1 ton is between C and N, okay, we calculate from the right. Then Nn equals 0, Qn equals minus YB, Mn equals plus 6 pi b. When the load is between N and E, calculate from the left. Then the normal force is 0, shear force equals YA, moment equals YA multiplied by 4. For section M, okay, we have for section M, we have the reaction here YB, so it's 0.6 pi b this way and 0.8 pi b along the field. For section M, and for section G in the column, section N, and for section G in the column, normal force equals 0.8 G. Normal force equals 0.8 G. Shear equals 0.6 minus 0.6 pi b, and moment equals YB multiplied by 1.5. This is at 1.5, 2 meters vertically, or 1.5. So this is for section G. Okay. So now N at G equals minus 0.8 pi b. Q at G equals minus 0.6 pi b. M equals 1.5 pi b. Okay. So influence line of YB is 0 to 1, 0.4 over here, and minus 0.2 from similarity triangles. For YA, 1 to 0, 0.6 similarity triangles extend 1.2. Influence line of NN doesn't matter where the load is, NN is equal to 0 because the reactions are X equals 0, so NN equals 0. QN, like what was done before for the beam, minus 0.4 to 0 plus 0.6 to 0, which is 4 over 10, and this one is 6 over 10. So 0.6 to 0 plus minus 0.4 to 0 plus extend. Influence line of MN, like what was done before, AB over L, which is 6 by 4 divided by 10, plus 2.4 to 0 extend to minus 1.2. Influence line of NM, normal force at N again is M is 0, doesn't matter what the load is. The reactions are always 0, so N X's are always 0, so NM equals 0. QM, when the load is between here and here, Q equals minus 1, and it is 0 beyond, because when the load is here, there is no load in the cantilever, so calculate from the left, it is 0. So now emphasize NQM, minus 1 to 0 at M and 0 beyond. Minus 1 constant and 0 beyond. Influence line of MM, minus 2 when the load is here, 0 when the load is here, 0 for the rest of the beam. Influence line of energy, like what we've seen, calculated, 0 to minus 0.8, 10 to 16. Influence line of reaction, 0 to plus 0.6, minus 0.12. Influence line of energy, 0 to 1.5, minus 0.3. We're done with the example, we're done with the lecture, and I'm going to solve more examples starting on page 14 in the next lecture. We'll see you then. Thank you very much. Bye.